a page, a paragraph entitled Distribution in the Mu Space. You remember last week we started the subject of, and we introduced the concept of the ensemble. The ensemble is a replica of the same system replicated many times, because we do not have enough information about the state of the system. This is the typical case in which the number of particles that we are dealing with is so large that it becomes impossible to describe individually the dynamics of each particle. Obviously, the different replicas of the system that we have in the gamma space, they do not interact with each other. Okay. To calculate the entropy, it is preferable, we did not introduce this last week, but we do it now. It is preferable to introduce another space that is in some sense simpler, because it's a space in which the coordinate are as many as the degree of freedom of the individual particle that belongs to the system. So we take a simple case in which the particles of the system are of the point-like type. That means that they do not have internal degrees of freedom, okay? If you consider, okay, obviously molecules are particles with some position and momentum associated to the center of mass. But then molecules, being constituted of several atoms, they may have internal degrees of freedom. For instance, they may vibrate, okay? Instead, we consider a gas of particles that is made of point-like particles. So each individual particle has only 3 degrees of freedom, that is the position of the particle itself. And then, of course, we have other 3 coordinates that are the 3 components of momentum. So the phase space of the individual particle has 6 dimensions, okay? Instead, the phase space of the whole system has 2s degrees of freedom, okay? In which s is the total number of degrees of freedom of the total system. So to distinguish these 2 spaces, you remember we called the phase space of the full system, we called it gamma. Gamma stands for gas. It's the initial of gas. Instead, the space that we are considering now, it's called mu. Mu stands for molecule, okay? Given that the procedure by which we proceed is just the same as we did last week. First of all, we subdivide the mu space into cells. And these cells have a size that is selected in order not to violate the uncertainty principle, okay? So along the coordinate axis, we have the side of each cell, delta Q, and along each momentum axis, we have the side of the cell equal to delta P, and the product, delta P times delta Q, is of the order of the Planck constant, as you remember. So the volume of each cell is delta Q to the cube times delta P to the cube. So delta Q times delta P is H, the Planck constant. So the volume of each cell is H to the third. In the page, it is H to the sixth, but it is a misprint. So it is H to the third power, okay? What is the fundamental difference between the description in the gamma space and the description in the mu space? The difference is that in the gamma space, since each point describes the total system, all points are simply different replicas of the system. So they do not interact with each other. They are like different images of the system that are complying with the constraints of the system, like they have the same total energy and so on. Instead, in the mu space, the points of the mu space are the individual particles, so they do interact with each other. Particles may collide, and during the collisions, they may exchange energy and momentum. Okay. At this point, we assume that the total number of the particles in the system is equal to n, capital N. Then, as we did before, we number the cells. So we ascribe an index R to each cell. And then we call nr the number of particles that at time t belong to this cell number R. Of course, this nr may be 0. Some cells may have no particles in them. And it may also happen that all particles are in the same cell. So in that case, the population of that cell would be equal to capital N and all the rest would be 0. Okay. Then we take the average of the dynamic quantities over the particles of the system. So you remember the average of the ensemble was indicated with a complicated symbol that is in equation 176. The average of on the ensemble was F sub gamma of the dynamic quantity A. The average over the particles of the system is indicated with a much simpler symbol that is A bar. And it is defined, of course, as 1 over n times the sum of the products of the populations nr times the value of the dynamic quantity of interest. This dynamic quantity could be any dynamic quantity, that is any function of position and momentum. Okay, so maybe it could be the energy, for instance. Okay, so the energy, if A is the energy, then we calculate it considering in each cell the coordinates Q and P of the center of the cell. And then we ascribe to A the same index of the cell. Okay. Obviously, A sub R has no explicit dependence on time. Okay. Instead, the populations and sub R may depend only on time. Okay. If we consider the ratio nr over n, obviously this is a non-negative number that is smaller or equal than 1. Okay, so it is the fraction of particles that belong to the cell number R. Okay, At this point, we define the entropy of the system. And the entropy is one of the possible types of averages that we have in our system. The entropy is defined by selecting for the quantity A sub r, we select the log of P. P is the fraction of the particles of the system that belong to cell number r. So PR is a number that is between 0 and 1. So the average of log P is called HB. HB is called, takes the name of Boltzmann's H function. This is not the entropy. The entropy is defined as minus the Boltzmann constant Kb times Hb. We already made a little discussion about this in the last lesson. Now I have added a figure to the notes. And the figure that you see on the screen is simply the form of the function PR times log of PR. Okay, obviously, if PR is equal to 1, this function is equal to 0 because the log is equal to 0. If PR is equal to 0, then log of PR goes to minus infinity, but PR is stronger than the log of PR, so the 0 wins. And we have again 0. And if PR is anywhere in between 0 and 1, of course, the log is negative. So in conclusion, the function PR log PR is non-positive and has the shape shown here in the figure. As a consequence, the entropy that has a minus is non-negative. It is just proportional to the curve that you see here, but it is mirrored. Okay, so it's the, instead of being concave, it is convex. Then the idea is we want to calculate the time evolution of entropy. And of course, we can equally well consider the time evolution of the function HB. And in order to do so, we take the derivative of HB with respect to time. We already calculated this quantity. And after a very simple calculation, one finds that the derivative of h with respect to time is the sum of 1 plus log PR times the derivative of PR with respect to time. Of course, this is of little help because we have expressed the derivative of HB in terms of the derivative of PR, and we don't know the behavior of the derivative of PR, okay? So a possible solution is that we consider the dynamics of each particle in the system, and then we calculate at the end of this calculation the derivative of PR. So we can simply use the standard laws of mechanics, okay? But this, as we said before, is impossible because if we have a system with many molecules or many atoms, the quantity of calculations that we should perform is unsurmountable. So we cannot do this, and we must resort to another approach that is of the probabilistic type. So we introduce a concept that is what is the probability that a particle that is initially in a cell, like cell of index S, changes the cell and goes into the cell of index R. Okay. So we introduce this quantity that we don't know anything about for the moment. We call it, as you can see here in the text, WSR. That is a non-negative quantity. And this is the unconditional probability per unit time that a particle makes a transition from the cell of index S to the cell of index R. Of course, it is interesting only to consider the case in which a particle changes the cell, okay? The situation in which the particle stays in the same cell is of no interest. In principle, there is also a probability W with the two indices equal to each other, like WSS, okay, but it is of no interest. It does exist, but it is of no interest, okay? Why do we say unconditional? Unconditional means that we can do a separate calculation by which we determine this probability per unit time, regardless of the actual possibility that the transition occurs. Okay, for instance, you remember that in quantum mechanics there are states. Okay, and if you consider electrons, okay, one electron can, when one state is occupied by one electron, there is no possibility for another electron to enter the same state, okay? So we can calculate the probability because it is a separate calculation, but then we check if the state is already filled, then there is no way for the particle to make the transition. So there is the probability, but then this probability must be multiplied by the quantity of states that are free. If there are no free states to be occupied, then there is no transition. Okay, so this is why we call it unconditional. Given that, if the total number of particles that is in the cell number S at some time is equal to ns, and since each of these particles has the same probability of making the transition to the other cell, the cell number R, then the total number of particles that actually do make a transition from the cell number S to the cell number R is the product of the probability times the number of particles that are initially in the cell number S. That is the number of particles that in principle could start a transition. Okay? So WSR times NS is the number of particles that at time t and in the unit time makes such a transition. In order to calculate the total number of particles that enter the cell of index R due to the transitions, we of course must sum up over index S. Okay, and this sum will provide the information about the increase in the population of the cell number R. On the other hand, so the sum we are talking about is the first sum at the right-hand side of equation 180. Okay, the first sum is what enters into cell of index R due to the transitions of particles that come from outside. But at the same time, there could be other particles that are initially in the cell number R and make a transition that brings them outside of this cell. Okay. Obviously, this is given by the second block of equation 180. That is, we take the probability WRS. You see that the two indices are swapped. So the initial state is R and the final state is S. So WRS is the unconditional probability per unit time that the particle that belongs to cell number R makes a transition from the cell R to the cell S. And then we multiply by the population NR, okay? In these two sums, we may also have terms with equal indices, S, S, or RR, okay? But of course, they cancel each other in the sum. So as I said before, they are irrelevant, okay? So can we calculate WRS? Yes. And of course, WRS depends on different factors. For instance, we may have external perturbations that act on the particles so that they are induced to make transitions, okay? So the first idea is that we have external forces acting on the system of particles. But then there is another possible reason for the transitions, that is the particles have collisions with each other. So the particle of the system travel for a while without being involved in any collision, but from time to time they collide with each other. And during these collisions, of course, they exchange momentum. Since they exchange momentum, the momentum coordinates change, and they move from one cell to another. The collisions are point-like. So during a collision, there is no change in position, okay, because the collisions between point-like particles occur in a single point of the space, and they are instantaneous, okay? So in a collision, there is no change in the physical coordinates, but there is a change in momentum, okay? Now, we don't want to calculate the entropy of a system that is subjected to external perturbations, because then we should consider the external perturbation, and they could be of any type, okay? So the entropy of the system that is not isolated is of no interest. It is of interest the entropy of a system that is isolated, that is a system that is not subjected to any external influence, that is the system is something that is trying to go to equilibrium, okay? In that case, we have only that the change from one cell to the other is produced by the collisions, okay? Then we can use the procedures of quantum mechanics to calculate the probabilities W, R, S, R, okay? And one of the conclusion of the quantum mechanical calculation is that the probabilities are invariant upon the exchange of the indices. That means that WRS is equal to WSR, okay? This is important because we can simplify 180, if we use the same symbol for WSR and WRS, so we collect W. And then we divide by the total number of particles of the system. So instead of using the populations NR and S, we use the fractions PR, PS. Eventually, as you see in 181, we are able to express the derivative of the fraction PR, that is the quantity that we want to calculate, in terms of the fractions PS and PR and the probability WSR. Okay. Then we insert this into the expression of the derivative of the Boltzmann H function. So we obtain 182. Okay. So at this point, we have an expression in which only the fractions p appear. Okay. From now on, it is a purely mathematical manipulation. Okay, there is no physics involved anymore. You see that 181 contains a sum over index S. But then we insert 181, as you remember, in 179, in which we already have another summation over index R. So eventually we have a double summation that is visible in equation 182. We have a double summation over the two indices R and S. Okay. Of course, this double summation spans over all the cells of the phase space, okay, from 1 to infinity. R and S go from 1 to infinity. So we can equally well represent the same quantity by exchanging the indices, okay? So if you look at equation 183, it is just the same as equation 182, simply S has become R, R has become S. On the other hand, W is invariant, so we can still call W with the two indices as R, S in the first position, R in the second position. And of course, the sum has the two indices, and also the position of the two indices is irrelevant. Okay. So 182 and 183 are two formally different but legitimate expressions of the derivative of HP. Of course, since 182 and 183 are equally good, we can take the sum and divide it by 2. So we obtain a third expression that is also equally good. Okay, so we take the sum of 182 and 183 and then divide the total by 2. We obtain the same thing. Why do we do so? It looks silly, but the reason is that in so doing, we eliminate the unity here and there. So conclusion, the final expression after this manipulation of the derivative of the Boltzmann H function is 1/2 sum over the indices of log PR minus log PS times the probability times PS minus PR, okay? Now, we are interested only in practice, only in the sign of this result. We want to see whether this derivative is positive, negative, or depending, okay? Well, W is a non-negative quantity because it is a probability per unit time. Then you see in the parentheses, in the last term, we have PS minus PR. So this parenthesis is either positive or negative, depending on whether PS is larger or smaller than PR. The log of PR minus the log of PS, that is the first parenthesis in the sum, again is positive is if log of PR is larger than log of PS or vice versa, okay? But you see that in the first parenthesis we have PR first and PS second. And in the last parenthesis we have PS first and PR second. And the logarithm is a monotonic function of the argument. So if PR is larger than PS, then the log of PR is also larger than log of PS. That means that if the first parenthesis is positive, the second parenthesis is negative, and vice versa. Okay. So this sum is made of terms that are always negative, with only one exception, that PS is equal to PR. In that case, the summand is 0. Okay, one of the summand may be 0, the one in which S and R are equal. Okay, all the other summands are negative. Okay. Conclusion: the evolution in time of the Boltzmann H function is such that the time derivative is always negative, so this or non-positive. And when we remember that the entropy is proportional to HB with the minus, it follows that the time derivative of the entropy is always non-negative. There is a misprint. There is SB, there is no B, it's just S, ds over dt, okay? The conclusion is the entropy of an isolated system can only increase, which is a very well-known result of the macroscopic thermodynamics. You remember that if you take any system, you perturb the system so that you can impose an initial condition that is any condition of non-equilibrium of the system. And then you let it go. You isolate the system. We stop perturbing the system from the outside. So the system left to itself goes to equilibrium after some time, okay? And this is, of course, an irreversible situation, okay? You have that a system left to itself goes to equilibrium, and it never happens that a system left to itself and being in equilibrium gets out of equilibrium. That never happens in experiments, okay? So this is a very important and fundamental result and takes a name. It is called the Boltzmann H theorem, okay? This is such a familiar outcome that it takes time to detect the existence of a contradiction in this result, because you remember we examined a few lessons ago, we examined the properties of invariance of the equations of motion. You remember we said if the Lagrangian is invariant with respect to the shift in the origin of the reference, then the total momentum of the system is conserved. Or if the Lagrangian is invariant upon rotation of the reference, then the angular momentum is conserved. And we also said if the Lagrangian is invariant upon the change of sign of the time, then the total energy is conserved. Okay. Well, we have an isolated system. The total energy is conserved. And the equations of mechanics that describe the system are invariant if we reverse the sign of the time. So the individual laws that describe the dynamics of the single particle are reversible. If we go backwards in time, we follow the same trajectories of the particles in the phase space as we did when we went forward in time, okay? So this is a paradox because each individual particle is subjected to dynamicals law that are reversible with respect to time. And instead, the calculation that we just performed entails irreversibility of the physical mechanism because the system goes to equilibrium and does not come back out of equilibrium anymore. Okay? There is another contradiction because there is a theorem of mechanics that is the so-called Poincaré time recurrence, okay? And the Poincaré time recurrence is a theorem that states that every finite mechanical system, given enough time, returns to a state, a dynamical state, that is arbitrarily close to the initial one. Okay, so that means that if we take a system of particles and let it go, we keep it isolated, and we wait enough time, sooner or later, the system will come back arbitrarily close to the initial condition. The time that is necessary to come near to the initial condition is called the Poincaré cycle, okay? And also this situation is in contradiction to the H theorem that we have just demonstrated, because, of course, it is impossible, since entropy can only increase, okay? It is impossible that the entropy decreases back to the initial value. So this is a contradiction, okay? We may try to have a further insight of the question if we use a very simple model, okay? So we now try to get out of the contradiction, essentially, okay? We have 10 minutes left. We shall start now. Then we take the intermission. We'll complete the analysis of the contradiction in the second hour. It will not take too long, and then we shall interrupt the lesson because, as you remember, we have to fill the evaluation form. So in order to analyze the contradiction, we consider a very simple model that is called the Cox ring model. And the ring model is based on this picture here, okay? So you have a circular frame, and this frame is divided into equal arcs. So in this figure, the number of arcs is 16. Inside each arc, there is an object. And this object may belong to one of two possible states. We can call it 1 or 0, or we can call it white or black. So in the figure, the object are the circles, the little circles, and the state is the color. Then at each time step, there are equal time steps, one after the other. At each time step, all objects move clockwise synchronously by one arc. Okay, so each object moves one step in the clockwise direction. Okay. Finally, along the circle, there are a few markers. These markers are the magenta blocks. So in this figure, there are 4. The number of magenta blocks must be smaller than the total number of arcs. Cannot be equal. Okay. When one of the objects crosses the position of a marker, it changes its state. So for instance, I'm pointing with the mouse this object. When this object goes clockwise to the next position, it will cross the position of the marker, and then from white it will become black. Okay. In the next cycle, this black point will be here. On crossing the marker, it will become white, and so on. Instead, the other objects that, when moving clockwise, do not cross any marker, they keep the initial color. Okay. So in order to make the picture more poetic, sometimes people say this is a circle in the countryside. The object are sheep, so they can be black sheep or white sheep. And the markers are fences. So when a sheep has to jump over a fence, it will suffer some psychological stress and change color from white to black or vice versa. Okay. Now, the practical calculation that we can perform is this. We impose an initial condition. So we impose the position of the black and white objects, then the position of the markers, and then we calculate the time evolution of each object. Okay, we want to check what happens to the individual object in time. Of course, as long as the number of objects is small, like in this case, we can do it very easily. Okay, this is a very easy analysis that we can program on a computer. Okay, but if the number of objects becomes larger and larger, then, it becomes more and more difficult to do the calculation. So what we could do is a less precise calculation. That is, we simply check how many objects are white and how many objects are black at each instant of time. So we renounce the information about the actual position of each white object and each black object. We just want to know how many white of them are white and how many are black. Okay, so this is a less precise calculation. Okay, now we stop. We shall start again at 10:10. The conclusion of this analysis will be made in a very short time, and then we will proceed to devote about 20 minutes or 25 minutes to the evaluation forms. So we stop now. Okay, so we start again. Let me share the screen. Okay, so we were considering this ring, and we observe immediately that this situation is obviously reversible. So if you, after rotating clockwise for a while, if you go back and you start rotating counterclockwise the system until you go back to the initial condition, it is of course reversible. You restore exactly the initial condition. So reversibility is present in this model, obviously. Also, this model fulfills the Poincaré cycle because it is intuitive that after one full rotation of 2 pi, if the number of markers is even, you restore exactly the initial condition, because when the number of markers is even, each object will cross an even number of markers, so it will change color an even number of times. In conclusion, it will keep the same color as in the initial condition. If instead the number of markers is odd, then you need 2 rotations, 2 full rotations in order to restore the initial condition. So in any case, this model is reversible and fulfills the Poincaré theorem, okay? Then let's see what happens when we calculate numerically the population of the white and black dots. Of course, in a numerical calculation, we can use a much larger number of objects. So this is a numerical calculation. Let me expand the thing. Okay. This is a numerical calculation in which the total number of objects is 4,000. And all objects were set to the state equal to 0 at the beginning, at t equal to 0. So all objects were 0, okay? Then the thin line shows the time evolution of the number of 0 state when the number of markers is 32, and the thick line shows the same thing when the number of markers is 16. Obviously, if you had 0 markers, the object would stay forever in the 0 state, okay? So it is intuitive that the curves should go down when the number of markers increase. But the issue is that apparently you have a saturation. So this situation seems to show that actually the system goes to equilibrium after a number of time steps that is not so small. There are 800 time steps, as you can see from the horizontal scale. And when you have 16 markers, then the total number of zeros tends to a, let's call it an equilibrium value that is around 3,300. If you look at the extreme right of the figure, that means that we have about 700 one states. And if the number of markers is 32, then the number of zero states saturates to a value that is somewhere in between near 2,700. Okay. So this looks contradictory because the formal analysis that we did before shows that the system is reversible and should fulfill the Poincare cycle, whereas this figure seems to show that the system is fulfilling the increase in entropy that we calculated with the Boltzmann H theorem. So it seems that the contradiction is still there, okay? However, it is not so. And the reason is simply that the number of time steps was not sufficient, okay? We stopped the simulation here after 800 time steps. What happens if we just keep going, okay? If we keep going, we get this. So the figure that we were looking at before was stopped at 800, that is about here, okay? So it looks like it saturates, but it does not. If we keep going, since the number of markers is even in both cases, we expect that after one full turn, and you remember in this case we have 4,000 objects, so the total number of arcs that we should rotate in order to have a full rotation is 4,000. So we need 4,000 time steps. And after 4,000 time steps, we go back exactly, as you see here, to the initial condition, okay? So this model is reversible. It does fulfill the Poincare cycle. It looks like it does not. It looks like the entropy is increasing simply because the number of steps that we were considering was too short, too small, okay? So now the question is, but how long should we expect the Poincare cycle to be? Well, the Poincare cycle is enormously long. There is a note here that if you have a system made of n objects, okay, it is possible to estimate the Poincare cycle, that is the time that is necessary for the system to go back near to the initial condition. And it is of the order of exponential of n. where n is the total number of particles or molecules in the system, okay? And this time in typical situation is longer than the age of the universe. So this is the reason why we never see the conclusion of the Poincaré cycle, because this time is enormously long, okay? Yet, you may still be unsatisfied by this conclusion because the Boltzmann H theorem tells you another thing. It tells you that eventually that the entropy can only increase. Okay, so this seems to be contradictory with the rest. Okay, why is it so? And the reason is the following. When you calculate the evolution of the entropy of the system using the Boltzmann H theorem, at some point you give up with the dynamical description of the motion of the particle and introduce the concept of probability. This is the point in which we are introducing a difference in the calculation. We introduce the concept of probability and we give up with the mechanical equations. Okay? So we give up reversibility ourselves by introducing probability. Okay? If we do not introduce probability, we are in the conditions of this model, and this model predicts reversibility. So actually, the physical situations are reversible. It is difficult to observe reversibility because of the many influences from the environment on a system, okay? But the laws of mechanics are reversible, and also the laws of quantum mechanics are reversible because the Schrödinger equation, okay, that is the Schrödinger equation dependent of time, that is the quantum counterpart of the Hamilton-Jacobi equation of classical mechanics, is also reversible in time, okay? So it is that the continuous influence from the environment makes it impossible or very difficult to detect reversibility, but reversibility is in principle there, and this is important in view of some considerations that are necessary for introducing quantum computation. So now we stop for a while with this subject because now we have to proceed with the evaluation forms. So let me I have to find the instructions. Okay, for a while I'll have to do some operation on the system, but I'll explain it to you. So I have to enter the evaluation environment. Okay. Okay, so the system is presenting me with two classes because this course is made of two modules, and one module is of 30 hours and the other module is of 60 hours, okay? So what I shall do is I will open the evaluation for the module made of 60 hours because I have no other possibility. Before that, I want to show you a page. You remember, probably you don't remember because for many of you, this is the first time in which you have to fill the form. The form is very important because it is the only method for us to have a reaction from the students about each class that is delivered by the program or the faculty, okay? So please take your time, look carefully through the questions and try to answer at best the questions, okay? The questionnaire or the form is made of two types of questions. One are fixed. That is, you have to put a cross somewhere, okay? So the possible answers are predetermined and you have to cross one of them. The second part of the form is free, okay? And the free part is also very important, and for this reason that at some point in the form you will be asked how much you appreciate the individual class or the full program, okay? You can put something between 0 and very much. However, if you do not provide the reasons for this, it is very complicated for us to understand why you appreciate or not a class, okay? So in the free part of the questionnaire, I'm now sharing the screen. You should be able to see a page of a PowerPoint file, okay? Apart from the date that is long, okay? You may see questions like specific appreciation of the course, global appreciation of the whole program, okay? In the free space, please add the reason, even if your appreciation is high, okay? Also, there is another question that I like to ask the students. It's a provocative one. And that is the following. If you could travel back in time and this class was elective, would you still choose to attend it? Yes or no? And please add also the reason for yes or no, okay? So now I will let it go. So I will open. Then I have to fill a place. How many of you are present at this very moment? Because the system will distribute as many forms as the students. So it's 9 students present. So I'm going to open it for it tells me that it is open. That means that you should have received okay. Now you should connect to one address that I'm going to introduce in the chat section, okay? Let me write it down. The address is https val it. So you should access this address. I'm looking at the chat line, so if there are any problems, you can write something or open the mic, okay? At this point, probably when you enter the system will ask you a code. So I'm putting the code into the chat line. VPK TV. Okay. From now on, you have about 20 minutes. If there are difficulties, please drop a message into the chat line. Okay, now I'm going to close the form. Let's see what happens. Okay, so yes, all students have answered, filled the form. So I shall now proceed with the conclusion of this. Let me check what I should do. Okay, apparently the system is happy. Hope that it worked. Okay, so now it is 11, so we stop for 10 minutes and we shall restart with the class in 10 minutes. Okay, so we start now, and you should be able now to see a page entitled Quantum Computing. We start with some introductory considerations. Quantum computing is, as you know, the application of concepts derived from quantum mechanics to the information theory, or more specifically to the computational problems. And there are concepts that are typical of quantum mechanics that enter this issue. One is the superposition of states that you remember when we described the wave function. Interference, that is another aspect, okay, of the properties of the wave function. Uncertainty, that is something that you know very well. And then there will be also correlation and non-clonability. Clonability is the impossibility to reproduce, okay, a system because if we want to reproduce a system, we have to interfere with the system, and we destroy part of the information in the system. In order to introduce these issues, it is necessary to start with some description of the classical theory of computation. The formal theory of computation is traditionally considered something that started in 1900. And specifically with the so-called 10th problem of Hilbert, that is also called the problem of decision. You may know that the mathematician Hilbert, in a conference of mathematics that was held in 1900, at some point provided a list of mathematical problems that, in his view, were the most important problems to be solved in the next years. Okay, some of them have been solved, some of them did not. And one of them was number 10, was the following problem. Is it possible or not to find a general algorithm that in a finite number of steps is able to decide whether a Diophantine equation has a solution in terms of integers, okay? In algebra, a Diophantine equation is a polynomial with integer coefficients having a finite number of unknowns, okay? And the problem is it possible to find integer solutions to the equation, okay? By the way, there is a note here saying that the answer to the problem is negative, okay? And in order to find the answer, they had to wait 17 years, okay? 70. So the answer was found in 1970, okay? But the issue remains, okay? The issue is to find an algorithm able to solve a problem in a finite number of steps, which reminds us of something that is purely mechanical, okay? So at the time of Hilbert, there was no concept of mechanical procedure, but a number of years later, around 1936, 1937. Another mathematician, Alan Turing, proposed the formalization of the working scheme of the algorithms, okay? And the formalization consisted in decomposing a calculation procedure in a set of fundamental blocks, okay? This decomposition was given traditionally the name of Turing machine, and it provided an axiomatic and fully abstract description of a mechanical procedure. So the Turing machine is very simple. There is, you can see the scheme here. There is a tape of infinite length. Essentially, this is the memory. In the modern language, this is the memory. So the memory of computers is not infinite, and now it is very large, okay? And in the tape, there are boxes, and each box there can be a symbol, and the symbol is either 1, 0 or a blank. Okay, so B here stands for blank. Okay, then there is a head. The head can move along the tape and is able to read or write the content of the cell corresponding to the head. The head has an internal state and also contains a list of instructions, and the instructions are, in modern language, the program, okay? So what is the task of the program? The program must specify, given the state of the head and given the bit that is present at the location corresponding to the head, okay, the program specifies whether the bit should be changed or not, and also should specify in which direction the head should move. So it must specify the next operation performed by the head. The system has an internal configuration or state that is the condition of all components at some instant, okay? And then it performs the actions at each time step. So we take the time steps, we number them, we give them an index. At some point, the operation of the machine will stop. So the last time step will be called Tn, okay? That is the end of the program. The initial time is T0, the intermediate times are Ti, okay? And the operation that is carried out at time Ti is indicated here with omega I, okay? So an algorithm implemented in the Turing machine consists in performing one or the other of the operations that are listed here. That is, the head moves one step to the right or one step to the left, writes a symbol taken from a list of symbols into the cell corresponding to the position of the head, or erases the symbol. And finally, the program stops. Okay, it is important that there should be a condition at which the program stops. Okay. So this is a very simple description, but it is the basis of all computers. What does it mean? It means that given enough time, the Turing machine can perform any program or bring to an end any program that is also doable by a supercomputer. Okay, a supercomputer will take less time. A Turing machine will take a longer time because it is simpler, but it is equivalent. Okay, so a Turing machine can carry out all elaborations that are possible within the existing models of calculation. Okay. The issue in general, not only for the Turing machine, but for any computer, is how long does it take to complete a calculation? And qualitatively, we may answer that it depends on how much or how complicated is the problem. So this leads to a classification of problems that goes under the name of computational complexity. Okay. So the issue is it practically possible to bring a computational problem to an end? Okay. And it is very easy to find problems such that the quantity of calculations that is necessary to complete a problem is so large that the task is unaffordable. Okay. So the typical benchmark to describe the complexity of a computational problem considers two classes of problems. One class is so-called the class of the problems that have a polynomial complexity. And the other one is the class of the problems that have a complexity that is non-polynomial. And the typical situation, we shall give an example immediately, is that of the problems that are of combinatorial complexity. Okay. A typical example of a problem that has a combinatorial complexity is the so-called problem of the traveling salesman type. Okay. That is formulated very easily. We have this gentleman that is the traveling salesman who has to travel through n cities. So there are n cities that are given. Then there is also another information that is the mutual distance between each pair of cities. Okay. And this gentleman must visit each city exactly once and finally come back to the original city when the travel started. Okay. And the issue is to find the shortest route that goes through all cities once and goes back to the original one. Okay. Another distinction that is important is the distinction between a deterministic and a non-deterministic algorithm. Okay. A deterministic algorithm constructs the demonstration of the result by considering all possibilities. So it demonstrates the theorem, okay? by considering all possibility, we essentially demonstrate the issue or the theory. Okay. So going back to the traveling salesman problem, the algorithm that solves such a problem must consider the total possible routes connecting n cities. And one can immediately see that the total of possible routes is n minus 1 factorial. This is why it is called of combinatorial complexity, okay? Because when you see a factorial, it's combinatorial problem. Then for each of these n minus 1 factorial roots, the algorithm should calculate the length of the route and then take the minimum. And this would be the solution of the problem. Okay. A non-deterministic algorithm instead is the verification of the validity of the theorem. Okay. So the theorem is given and the algorithm verifies the theorem. Okay. And this is typically of a polynomial complexity. Okay. An example is to given a number n, to find it whether it is a composite number or not. Okay. In either case, either the traveling salesman problem or the verification that n is a composite number, this number n is the indicator on which we have to base the analysis of complexity. Okay. If we have a problem of extension or size equal to some number n, if the amount of work that the computer should perform to find the solution is a polynomial of n, then we say the complexity is of the polynomial type. Okay. So n is the dimension of the problem. Okay. Since we have to perform a calculation involving factorials, it is convenient to consider the Stirling, the so-called Stirling approximation of the factorial. Okay. When the integer number n is large, it is possible to demonstrate that the factorial of n is well approximated by the expression that you can see there. It is the square root of 2 pi n times n divided by e to the nth power. Okay, and this approximation is very good. Even if n is not so large, like n equal to 10, the approximation is already good within a few percent. Okay. So you see immediately that the traveling salesman problem grows exponentially with n, whereas the time necessary for verifying whether n is composite grows like a polynomial. Okay. Now, let's group the problems. The problems that allow for a deterministic solution of the polynomial type belong to a class that we call P. Then there is a larger class in which the verification is polynomial. You may remember the verification is somewhat easier than the demonstration. So the problems in which the verification is polynomial are called, that belong to a class that is called NP. So NP is larger than P. P P a subset of NP. And finally, the problems of the combinatorial type are called NP complete. And the short for it is NPC, okay? So just to give you an idea about what a combinatorial type is, let's consider it is in the note here. Consider an example that looks simple, okay? That is an example in which there are 26 cities to be visited, okay? And we want to find the shortest path that connects these 26 cities such that each city is visited once, okay? And because of that, we must examine 25, that is n minus 1, 25 factorial possible routes connecting the cities, okay? So let's estimate how long it would take to calculate this number of routes, okay? So we take a very advanced computer, okay? Very advanced to the point that the computer is a single atom, okay? So assume that we have been able to construct a computer that is a single atom, okay? You know that the radius of an atom is a few angstrom, okay? So assume that the radius of the atom is 3 angstrom. That makes 3 times 10 to the minus 8 centimeters, okay? And assume that the time that this atom-sized computer takes to calculate the length of one single route is equal to the time that is taken by light to cross the atom itself, okay? Of course, it will be a very short time, okay? So the speed of light is 3 times to the 10 to the 10th centimeter per second, okay? So the time necessary for the calculation of the single route is the diameter of the atom, RA, divided by the speed of light. That makes 10 to the minus 18 seconds. That's a very, very short time, okay? But now we have to multiply this by the number of routes. And the number of routes is the factorial of 25, okay? So if we use the Stirling approximation, okay, essentially in the Stirling approximation, we see that the log of n factorial is of the order of the log of 25, very, very crude approximation, okay? And if we use the Stirling approximation, we find that this is about 58, okay? So 25 factorial, that is the total number of the roots, is of the order of the exponential of 58. So if we convert it into the power of 10, is 10 to the 25th, okay? So the time necessary to calculate all roots would be the total number of roots times the individual time, that was 10 to the minus 18, it is 10 to the 7 seconds. That is about half a year, okay? Or 1/3 of a year, 4 months, okay? So with a supercomputer of this type, it would take 4 months to calculate the solution to the traveling salesman problem with 26 cities, okay? So this is an example of a NPC and non-polynomial complete problem, okay? Now we have to take a short resume of the Boolean algebra, still in the classical situation, so using the classical logic. I'm sure that you already know this subject, so I shall go quickly through it, because then, that is on Thursday, we have to start considering the quantum logic gate, okay? So I assume that you know what the binary variables are. We indicate them with symbols A, B, C. And what the binary function is, okay? It's just a suitable combination of the binary variables, and we call it Z. And you remember that every binary function can be expressed as a combination of the not, and or operators, okay? Operators are indicated with symbols and with a truth table. I have a few figures here that show this is the not operator, as you know very well. This is the AND operator with the truth table that provides all the possible outputs corresponding to the combinations of the input values of the logical variables. There you are with the OR operator. And here you have the implementation of the NOT operator that is, of course, made with the CMOS technology that you know very well. This is the simplest implementation, but it is obvious that even this very simple implementation, from the point of view of energy, is irreversible. The energy that is necessary to provide the operation of the simplest operator, that is the NOT operator, okay, the energy is lost because we inject the charges into from the bias VSS into the ground, okay, and there is no possibility to get back this energy. Another property that you should remember very well is that the AND and OR operators are commutative and associative. Another operator is the exclusive OR, that is somewhere here. There it is. The exclusive OR has the property that the output is 0 if the two inputs are equal to each other, whereas the output is 1 if the two inputs are different, okay? The exclusive OR is also commutative and associative. The symbol for the exclusive OR operation is the one that is visible in figure 6.3, okay? Also, there are other important operations that are the NAND and NOR operations, whose symbol and the truth table are visible below. I'm going to them in a second, but we stay on this formula because the NAND and the NOR operation are commutative, but they are not associative, okay? This is for the NAND, and this other equation is for the NOR, okay? Then you remember very well the De Morgan laws or De Morgan theorems. That is the negative of the product of two logical variables is the sum of the individual negatives. Negatives is also indicated with the term complemented. So the complemented end is the OR of the complemented variables. And dually, the complemented OR is the end of the complemented variables. Then there are other obvious relations that A plus 0 is A plus 1 is 1, A plus A is A plus complemented A is 1, A times 1 is A times 0 is 0, A times A is A, and A times complemented A is 0. Then there are the so-called contraction rules that are A plus AB can be written in the following manner. A is like A times 1. 1 is like B plus complemented B. Then you group A. B complemented plus B is 1. B plus 1 is 1, so you have A. Instead, A plus the product of complemented A times B can be written by exploiting the previous operation. So you replace A with A plus AB. Then you collect you collect B. A plus A complemented is 1, so you have A plus B. I'm going to upload this material. This is, as you remember, the symbol of the NAND operator. We also have the logical implication, but the logical implication will not be used later, so we skip it. This is the symbol and the truth table of the NOR operator. And this is the exclusive OR symbol and truth table. How should we implement physically some of these operators? Okay, we already consider the NOT operator. In this figure here, you see the NAND. So you see an implementation of the NAND operator on the left and of the NOR operator on the right using the CMOS technology. Okay. Question, why am I showing the NAND and the NOR operator and not, for instance, the AND or the OR operator? Because you may remember the NAND and the NOR operator are universal. We shall come back to this concept in a minute, okay? But before we continue, let's analyze a little bit what happens, for instance, with the NOR operator, that is the one on the right, okay? Assume that both A and B are 0, that means 0 volts that are grounded, okay? And of course, you consider the so-called positive logic, so you have that a 0 voltage or a low voltage correspond to the logical 0, and the high voltage, in this case VSS, is the high voltage, correspond to the logical 1. Okay. So if A and B are 0, then T1 and T3, that is the two transistors in the lower part of the figure, are off. Okay. That means that point Z, that is the output, is disconnected from ground. At the same time, transistors T2 and T4 have the gate that is high because the gate to source voltage is negative and high. That means that the two transistors that are of the p-channel type, the T2 and T4, the two upper transistors, are active. Okay. So the two upper transistors are active, but it is impossible for any current to go through them because point Z is open. So the only possibility is that point Z has the same voltage as the bias VSS. So when both A and B are grounded, Z is high, so it is a logical 1. Instead, when A and B are equal to VSS, then T1 and T3 are active, but T2 and T4 are off. So again, there is no current. In this case, because T2 and T4 are off. And the only possibility for the circuit to be coherent is that Z is equal to 0. Okay. Now we take one of the two input signals high, for instance A, and the other B equal to 0. That means that T3 is open, but T1 is shorted, that is active. Okay, so Z is connected to ground. And at least one of the two transistors, T2 and T4, is off. Okay, actually T2 is off because A is large. So Z is grounded. And of course, if we reverse A and B, it is still grounded. Okay, so this is the functioning of the NOR operators implemented with CMOS. In all cases, we have dissipation. Okay, so in all cases, these gates are irreversible. You may notice in these figures that we have dashed lines. There is a dashed line here near T1 on the left. Another is here. Another is here, and another is up here. Okay. These lines are the indicators of the bulk contacts of the transistors. Okay, so you may see an asymmetry because if you look at the left circuit, T2 and T4 have that the bulk contact is connected to the source. Okay. Instead, in T1 and T3, still on the left, the bulk contact is connected to ground. Okay, if you remember the practical structure, how the CMOS architecture is fabricated, okay? You remember that in the left case, T1 and T3 have the bulk contact connected to ground. This means that T1, in which the source contact is not connected to ground, has a source to bulk contact that can be different from zero and can also change depending on the operation of transistor T1. So transistor T1 has a body effect, has a threshold that depends on the source to bulk voltage, okay? And this is unavoidable. The same thing happens to transistor T4 in the right circuit, okay? The bulk contact of T4 is connected to VSS, okay? So it is different from the source voltage that is not necessarily equal to VSS. So also in this case, transistor T4 has the body effect. This is the logical implication, but we skip it. These are just examples of evaluations of the of calculations of logical function. Okay. Now we quickly devote the last minutes left to some example of number representation. This is really obvious. There is nothing that we should devote much time to, okay? You know what the decimal representation of numbers is. It is just a combination with integer coefficients of the powers of 10. So 19 is represented by this. 6903 is represented by this, okay? How do we obtain the coefficients? We just keep dividing by 10. So if we start with 19, we divide by 10 and the remainder is 9. Okay? after dividing by 10, we obtain 1. And if we divide 1 by 10, we obtain 0 with the remainder of 1. Okay? And then we multiply 9 by 10 to the 0 and 1 by 10 to the first power, and that's it. Here we divide 6903 by 10, we obtain 690 with the remainder of 3, then we divide by 10, we obtain 69 with the remainder of 0. We divide by 10, we obtain 6 with the remainder of 9, and etc. And then we multiply all these numbers by the corresponding power of 10. Okay. If we want the binary notation, we do the same. We simply express the numbers as the sum of powers of 2. So 19 is 16 plus 2 plus 1. 6903 is this more complicated sum. Okay. So in order to obtain the decimal representation, for instance, of 19, we keep dividing by 2. Okay, so if we divide by 2, we have 9 with the remainder of 1. 9 divided by 2 makes 4 with the remainder of 1, etc., etc. We obtain a strip of numbers, and then we multiply each by the corresponding power of 2. Okay, so we have that a representation of the number that in the decimal notation is 19, that is 19, would be this one. Okay. Next, we have to do the same with numbers that are between 0 and 1. Okay. So take as an example this number, 0.8125. Okay. Of course, we can express the same number as the negative, as a linear combination of the negative powers of 10. So it is 0.8 plus 0.01 plus 0.002 plus 0.005. That is this representation. Okay. And now we conclude, but obviously we find the coefficients in this case by multiplying the original number by 10, and we take the integer part of the result. So if we multiply this number by 10, we get 8. And the remaining one is 125. Then we multiply it by 10, we obtain this one, and we are left with 25, and so on. Okay? So now we stop. Of course, we shall do the same with the binary notation, and in the next class we shall find how to make the operations with the classical operators, and then we, in a short time, we go to consider the quantum operators. Okay, for the moment we stop. you.